Welcome. So we're going to be doing a worked example problem on power. This is the second worked power example problem. In this case, we're looking at a lift at a garage in which we're looking to determine how much power is required for the lift to raise your vehicle, estimated at 1.2 tons, 6 feet off the ground, and this lift is to be conducted in 15 seconds. So if we look at this as we can, initially, we can look at a Freebody diagram and observe the idea that there must be a lifting force, and we have the weight acting downward, and what we have is 1.2 tons, which we can multiply by the 2,000 pounds per ton to find that we have a weight of 2,400 pounds. Now what we have as a result is we have this balance, so we know that the force of the lift would also have to therefore be equal to 2,400 pounds in order for it to be lifting the car at a constant rate. And this is where we're assuming it's going to be done at a constant type of rate. In reality, we don't necessarily need it to be at a constant rate, but we're looking at what is the work done. And overall, however this lifting force is completed, it is completed such that it will create a lifting force of 2,400 pounds. The motion is also vertical, lifting at a distance of 6 feet. So what we have is the idea that we're ultimately looking at work done by a force over a distance. So we can look at this purely as the work that's done due to gravity. So we can say that the work in this case is equal to the change in potential energy. There is no kinetic energy. We're not creating an initial and final velocity that are going to be different. We're assuming it's starting from rest, being raised that distance, and it's still at rest then after the lift is completed. So we can essentially say there is no kinetic energy. So if we go with the idea that work is the summation of the change in kinetic energy and the change in potential energy from start to finish, from conservation laws, there is no need for this change in kinetic energy because essentially this is equal. We're told that the change in height is equal to 6 feet. So our change in potential energy, because we're raising it up 6 feet, W is equal to the mass multiplied by gravity, which is the weight. So that is our 2,400 pounds multiplied by a delta H. A delta H being 6 feet allows us to find that we get 2,400 pounds multiplied by the 6 foot height, allows us to find that we have work done that is 144. When we take the 6 times the 24, add in the additional 2 zeros, and we get 14,400 foot-pounds of work being completed. If we now return to the definition of power, power is equal to the work divided by the change in time. So in this case now we have 15 seconds of applied work. So we have 14,400 foot-pounds over 15 seconds. So in this case, as a result, 144 divided by 15 gives us 9.6. Multiply by the double zero, and we get 960 foot-pound per second. So we know that the power as a result is 960 foot-pounds per second. We can take this one step further, and if we recognize that there are 550 foot-pound per second equaling 1 horsepower, we can divide 960 by the 550, and we find that this is also equal to 1.745 horsepower. Typically, we do report the power in horsepower in US customary, so we find that we have 1.745 horsepower of power just applied.